Hello students, in this session we are going to deal with Mayer's formula. Mayer's formula has something that has to be done with molar specific heat capacity. In the previous chapter, while I was discussing about thermal properties of matter, I told about heat capacity, specific heat capacity, molar specific heat capacity. So just see that video one more time, so you will get into you can understand in detail what is meant by this. So here I am discussing about the molar specific heat of the gases, and then we will come to the Mayer's formula. Specific heat capacity for a given mole of gas is called molar specific heat. So for example, we can say like this: if I take gas, the gases have two types of specific heat. One is specific heat capacity at constant pressure, denoted by Cp, and the second one is specific heat capacity at constant volume, denoted by Cv. So gases has two types of specific heat, Cp and Cv, whereas liquids and solids, they have only one specific heat. So we are not categorizing them. What is meant by molar specific heat? Amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin or 1 degree. Amount of heat required to raise the temperature of 1 mole of a substance by 1 degree, that is called molar specific heat. So here molar specific heat at constant pressure, Cp, means what? The gas is held under constant pressure. Okay, here the gas is held under constant pressure during the heat transfer. Then the corresponding molar specific heat capacity is called Cp. Similarly, what is Cv? Volume of the gas is maintained constant. Okay, volume of the gas is maintained constant during the heat transfer. Then corresponding molar specific heat is called Cv. And in thermal properties of matter, that chapter I have discussed Cp greater than Cv. That also just view it once again, why Cp is greater than Cv. So I am not going to that again, I am just saying Cp greater than Cv. Mayer's formula gives the relation between Cp and Cv. I already told you Cp greater than Cv, so Cp minus Cv is equal to R for an ideal gas. This is actually Mayer's formula. Cp minus Cv is equal to R. That is Mayer's formula. So we are going to prove Mayer's formula. Okay, so first we can take the thermodynamic equations. First law, delta Q is equal to delta U plus delta W. That is the first law. Now consider the gas enclosed in a cylinder fitted with a piston. So when the heat is supplied, as I told you in the previous video, the piston can move up and the volume of the gas will increase. And if the volume is increasing, we can say work is done. Okay, we can say work is done. So the work done will be delta Q is equal to, delta Q is the heat, delta Q is equal to delta U plus P delta V. See, instead of delta W, I wrote P delta V. Now imagine imagine the piston is fixed and the piston cannot move further. At that condition, when it reaches the maximum condition, when the piston is fixed, at that condition what will happen? The volume will not change further. So, at that time delta V will be equal to 0. So, at constant volume delta V is equal to 0, and when delta V is 0, what can I write? Delta Q is equal to delta U, because delta V is 0, so this quantity becomes 0. Therefore, delta Q is equal to delta U. Now, we are going to find CV, specific heat at constant volume, CV. So, CV is equal to delta Q by delta T at constant volume. That means I am going to I am just differentiating this equation by delta T. Okay, dividing this equation by delta T at constant volume. So, delta Q by delta T at constant volume equal to delta U by delta T at constant volume, that is CV. We already studied internal energy is a state variable. So, it depends only on the initial and final state, right? Therefore, delta U by delta T at constant volume can be simply written as delta U by delta T. Okay, I do not have to mention whether it is constant volume or whether it is constant pressure, because internal energy is a state variable. Therefore, delta U by delta T at constant volume can be simply written as delta U by delta T. Now, listen what is on the LHS, CV. What is on the RHS? Delta U by delta T. Therefore, now I am getting CV is equal to delta U by delta T. CV is equal to delta U by delta T. Now, I am going to heat the gas at constant pressure, Cp. So, what I am doing? Cp is equal to delta Q by delta T at constant pressure. Okay, so this equation. So, when Cp is constant, listen to me carefully, when Cp is constant, there is a change in the volume. Cp means specific, molar specific heat at constant pressure. So, here which quantity is constant? Pressure. So, there is a change in the volume. Pressure is constant, there will be a change in volume. That means delta V will be there. So, take this equation and divide this by delta T. Here delta V cannot be 0, because I am going to heat the gas now at constant pressure. So, delta V will not be 0. So, dividing by delta T, Cp is equal to this delta Q by delta T at constant pressure equal to the second term, delta U by delta T at constant pressure, and I told you it is an internal state variable. You do not have to write constant volume or constant pressure. That is why I simply wrote delta U by delta T plus the third term, P into delta V divided by delta T at constant pressure. So, I divided this equation with delta T everywhere when the gas is heated at constant pressure. Now, we are getting like this, Cp is equal to LHS, it is Cp. In the RHS, LHS is Cp, in the RHS, delta U by delta T. What is delta U by delta T? Cv. Okay, delta U by delta T is Cv. So, instead of this, I am writing Cv plus P into delta V by delta T at constant pressure. This is my equation. Now, I want to give a substitution for this term. So, for that I take ideal gas equation. Ideal gas equation is PV is equal to RT for 1 mole of gas. Okay, for 1 mole of gas PV is equal to RT. So, differentiating both sides with respect to T. For constant pressure, here I am keeping the pressure, I am going to differentiate with respect to T for temperature, and here I keep the pressure as constant. So, when I differentiate this one, delta PV divided by delta T is equal to delta RT divided by delta T. Now, we are differentiating with constant pressure. So, from here I take pressure outside. Pressure is constant, so I take pressure outside. So, P into delta V by delta T at constant pressure equal to, here R is constant, I take it outside, delta T by delta T is 1. So, R. Okay. From the first term I take P constant, that is out. So, the remaining thing is delta V by delta T at constant pressure. Now, from the second time R is constant, I take it outside, delta T by delta T is 1. So, R. So, P into the final, and finally I am getting P into delta V by delta T at constant pressure equal to R. See, this is this term, no? This term, P into delta V by delta T equal to R. So, instead of this, what will I write now? R. So, Cp is equal to Cv plus R. So, from here take Cv to this side. So, Cp minus Cv is equal to R. This is Mayer's relation. Okay. This is the Mayer's relation. Cp minus Cv is equal to R, where R is universal gas constant. So, please take down. That's all in this session. Thank you.